All right, so we're going to continue this like balancing by half reaction business, but we're going to add a little bit of a twist on it. There's going to be this very key phrase that we're going to hear, which is under acidic conditions. All right, remember we talked about how acids were hydrogen ion donors. We did that example where we said HCl, when you put it into aqueous solution, it dissociates into these hydrogen ions, these chloride ions. All right, what makes acids acids is that they dissociate into these aqueous hydrogen ions here. Okay, so that key phrase, acidic conditions, means we have water and hydrogen ions floating around. All right, that's assumed to be present when we use the phrase acidic conditions. All right, so let's take an example here. I'm going to leave a bunch of space to make some sort of rules like we did last time. So I'm going to start my example down a little bit further on the page here. All right, whoops, not that one. All right, we have iron 2 ion reacting with what's called a permanganate ion, MnO4 with a -1 charge. This is a very common polyatomic ion. It's not one of the ones I made you memorize, but it's one that we'll see fairly frequently. This will react to create iron 3 ions and manganese 2 ions. All right, so we're going to kind of quickly here make our oxidation number table. We're going to be able to do this kind of quickly because 3 of these are super easy to assign, and the other one you would have worked out in problem 2, part B on your worksheet. So we can kind of fill in this table pretty quick. All right, I said 3 of these are really easy to fill in. Why are they so easy to fill in? What is the iron? Oh my gosh, sorry, not oxygen. I mean, we could do oxygen, but we want to do iron here. What is iron on the reactant side? +2, and how can we see that so easily? Because it's just the charge. What's iron on the product side? +3, and what's manganese on the product side? +2, cool. All right, so again, these ones were pretty easy. All right, so then based on what we did on our worksheet, what is the manganese oxidation number on the reactant side? No, go to your worksheet part. Okay, let's just do this together. Wonderful, MnO4 minus. Okay, the very first thing that we know, given our formulas here, is that my manganese plus these 4 oxygens have to equal that net charge of -1. All right, and now our goal is to start picking off. We have too many variables, so we're going to go and assign these oxidation numbers. All right, so again, this first part here, when we laid out our rules for our covalent compounds, was the sum of all the oxidation numbers needs to equal the net charge on the molecule. So that was that formula that we laid out. So now the next one is that hydrogen is going to be +1. Does that help us out at all? No, there's no hydrogen in this compound. So now we need to go to the next one, which is that the most electronegative element is going to have the oxidation number that's the same as the charge. So going back to my example here, I want to try to assign oxygen or manganese. Which one can I assign based on that electronegativity rule? Oxygen, our second most electronegative. Look, if there's one element whose oxidation number when it's in a compound you should just commit to memory, it's oxygen, all right? Oxygen is present in so many, think of all the polyatomic ions that we learned. There's oxygen there, right? Oxygen's almost always the most electronegative element in your compound unless it's paired with that one tug-of-war champion fluorine. But other than that, it's going to be -2 in its compounds. So now we have Mn plus 4 times that -2 gives me -1. So manganese -8 equals -1. Manganese has to be +7. Okay. Cool. So what's being oxidized and what's being reduced? Let's look here. Manganese is going down and iron is going up. If manganese is going down, what does that mean? Oxidized or reduced? Down, reduced. The other thing is oxidized. Okay, cool. So our first step is going to be the same as what we learned with our previous. Let me just under acidic conditions. Move this here. All right. First step is going to be the same as what it was before. We're going to break this up. Break up our chemical equation into those two half reactions. All right, so I'm going to use my oxidation table here. So again, sorry, break up that chemical equation into half reactions. All right, so I'm going to create an oxidation half reaction. And a reduction half reaction based on what we just did with our oxidation numbers. My oxidation half reaction is going to contain the elements that we said were being oxidized. So my iron 2 becoming iron 3. All right, everybody take a second. Give me my other half reaction with what was being reduced, the manganese. The MnO4- permanganate. It is used a lot because it is a very common oxidizing agent. All right, so my MnO4-, my permanganate on my reactant side, and that manganese ion on the product side. Okay. Cool, and so what we're gonna see, again, we said acidic conditions means that we assume there's water and hydrogen ions floating around. If we look at this reduction half reaction, you're gonna kind of see the difference between this and our previous example. All of a sudden on this side, I have oxygen atoms, and I don't have any on my product side. What the heck? Well, again, there's gonna be water and hydrogen ions present, and that's gonna come into play in this balancing, all right? First step, though, or next step, rather, is to mass balance all elements other than oxygen and hydrogen. Those are the special ones. What's up? Remember this term mass balance? What does that mean? Does anybody remember? That's our normal balancing, exactly, right? Normal balancing. Make sure you got the same number of, in this case, irons on both sides and manganeses on both sides. Okay? Let's look at our oxidation half reaction. All right, do I have the same number of irons on both sides? Yes, cool. We're going to look at our reduction half reaction. And again, for right now, I'm going to ignore the oxygens. I'm only going to pay attention to the manganese. Do I have the same number of manganeses on both sides? Cool. All right, so in this case, we're already sort of done with step 2. So now we got to deal with the oxygens and the hydrogens, right? That's what we've been kind of ramping up to. How do we deal with those elements that are just assumed to be there? All right, we're going to balance the oxygens with water. All right. So if I look at my oxidation half reaction, do I have to balance any oxygens? No. What about my reduction half reaction? Yes, I have 4 oxygens on my reactant side and none on my product side. So how many waters should I add to that product side? 4. Your water in this aqueous solution, what would my state of matter be of water in an aqueous solution? Liquid. So cool, now I've balanced my oxygens, and now I have a whole bunch of hydrogens on the product side that weren't on the reactant side. So now I just introduced a new problem here, okay? So next step, we balanced our oxygens with water. Now we're gonna balance those hydrogens using those hydrogen ions with H+. All right, so everybody take a second, see if you can't. Our oxidation half reaction, again, we don't have to worry about, but our reduction half reaction, you're gonna have to balance those hydrogens by adding H pluses to one side here. All right, which side do I add my hydrogen ions? The reactant side. And how many am I going to add? 8. Because each water molecule contains 2. And my hydrogen ion state of matter is aqueous. They are floating around in this aqueous solution here. All right, so just real quick. We said acidic conditions. We assume that water and hydrogen ions are present. And so we can see that in our balancing here. In our balancing, we just assume that there were waters. So we use those waters to balance our oxygens, and we use those hydrogen ions to balance our hydrogens. Cool. So now, everything, we're kind of back to regularly scheduled programming. You're going to charge balance. And then lastly, we're going to sum in such a way that we cancel those electrons. So charge balance with electrons, sorry. And then sum in such a way that our electrons will cancel out. All right? So given what we did with our previous example, take a second and see if you can't charge balance these two half reactions and then sum everything back up so that your electrons cancel out. do this one together here. We got to charge balance this reaction. It's kind of the easier of the two. So let's take a look at this oxidation half reaction first. What is the net charge on my reactant side? +2. And what about my product side? +3. I need to make these match one another, right? And the only thing I can do is add electrons. So which side do I add electrons to? Right? So the only thing you can do is make these numbers smaller by adding electrons. So I'm going to add electrons to my product side. Okay, now my net charge is +2 on both of these. All right, let's do this product side of our reduction half reaction first. It's a little bit easier. My manganese ion has a charge of +2, but I also have these 4 water molecules. Each one has a charge of what? 0. Water is neutral. There's nothing written up here. So that means my net charge over here on my reactant side is +2. On product side, sorry. If we jump over back to our reactant side, I have 8 hydrogen ions. Each one has a charge of +1. So what's the total amount of positive charge I get from those 8? Well, from these 8, I'll have 8, and then I'm going to add on the charge of that permanganate ion, and I have one of those with its -1 charge. So my net charge on this side is +7. All right, so where are we going to add our electrons? The reactant side, and how many am I going to add? 5. 5 electrons. Now when I sum this all up here, I'll have that charge of +2. Cool. All right, so now I want to sum these back up. What am I going to have to do to my oxidation half reaction first? I need to make sure that the number of electrons on my product side are equal to the number of electrons on my reactant side, right? But I don't just want to say, all right, make it 5 electrons, because now all of a sudden this isn't charge balanced anymore. We spent all that time charge balancing. So what we're going to do is we're going to take the entire thing and multiply it by 5, and then we'll sum these up. All right, I'm going to give you all a head start on trying to sum this up, and then I'll kind of quietly start filling in. All right, so now we get this big, ugly mess where we have these 4 different reactants and 4 different products here. Our 5 iron ions, 5 electrons, and 8 hydrogen ions, plus that permanganate will give us 5 iron, 3, 5 electrons, that manganese ion, and 4 waters. But what am I going to do to this equation before I'm done? I'm going to cancel anything that appears on both sides. You better always be able to cancel what from here? The electrons. Cool. You also may be able to cancel some hydrogen ions or some waters, depending on what happened previously in your balancing. That isn't the case this time. We're just going to get rid of those. All right, but you want to look out. If you had water on both sides, you could cancel some of them out. Cool. All right, so when you get to these last 2 pages of your worksheet, they will involve balancing these chemical reactions here. All right, this is what we mean by when we say under acidic conditions. We assume that water and hydrogen ions are present, and so that will influence our balancing here. All right, we got to break up into those half reactions. We're going to mass balance everything other than oxygen and hydrogen. Balance oxygen with water, hydrogen with hydrogen ions, and then charge balance with electrons. Okay, so this is what we mean by balancing under acidic conditions for these redox reactions. Cool. All right.